So next topic will be the thermal contact resistance. So the importance of this is if the contact between the two surfaces is not perfect, if there is any air gap or because of unevenness between the two slabs are existing, then the thermal contact resistance is going to be present and there will be a temperature drop. The temperature will not be same. There is a drop in the temperature and which affects the rate of heat transfer. So what are the important assumptions in the calculations of the composite wall? The contact between the adjacent layers is perfect. The contact between the adjacent layers is perfect. And at the surface interface, there is no fall in temperature. There is no drop in temperature. That is the second assumption we are making in solving the heat transfer through composite slabs. And at the interface, the temperature is continuous. And also there is no drop. There is a continuous temperature. The same temperature is going to be same. Although there is a discontinuity in the temperature gradient. So these are the three assumptions which we are making in the calculations of the composite wall or composite slab. But in real systems, it is not same. In real systems, it is slightly different because the slabs, two slabs may not be perfect or may not be, there may be unevenness or there may be some voids present or there may be some air gap between the two slabs when we are joining the slabs. So there may be air entrapped between the two slabs. So in the real systems. So due to that, the thermal contact resistance has to be calculated. So there is not a single plane of contact. The contact is going to change because of this all these parameters in the real systems. So the area will not be same and which is going to affect the rate of heat transfer. So which has to be taken into consideration. So in the earlier derivation, what we have taken, we assumed that the surfaces are in perfect contact. There is no gap between the two surfaces. There is no unevenness between the two surfaces. There is no air gap between the two surfaces. Then only we can use that equation. Suppose if any such systems are existing, then the area changes and the rate of heat transfer changes and the thermal contact resistance also there is a change. So something like this. If there is any air gap or there is any mismatch between the slabs A and B. So initially what we are assuming that this temperature T2 is only one temperature is there. But because of this air gap or unevenness, then there is a temperature drop between A and B. But in the earlier derivation, we are assuming that there is no temperature drop. They are perfectly matched. So temperature drop at the interface. Similarly, between the that is slab B and slab C. So if they are not perfectly matched, so there will be temperature drop. So these factors should be taken into consideration in the real systems. That's why whenever 2 or 3 slabs are combined, so you should take care of this. Otherwise, it is going to affect the rate of heat transfer calculations. So this temperature drop may be minute, maybe 1 degree or 2 degree or 3 degree, but that should be taken into consideration. So due to this reduced area and the presence of air voids, a large resistance to heat flow at the interface occurs. So what is going to happen here? So because of this area reduction and also the air voids, the resistance to the heat flow, the heat is flowing from one slab to the other slab or in this direction, right side direction. The resistance will be increasing here. There is a increase in the resistance at the interfaces. So which has to be calculated. This resistance is known as thermal contact resistance. This resistance is called as thermal contact resistance. So sometimes these calculations also should be taken into account. Otherwise, the rate of heat transfer to the composite slab is going to be affected, and it causes temperature drop. And what is the importance of this thermal contact resistance? The importance of the thermal contact resistance is it due to that the temperature drops between the two materials. There should not be any temperature drop, and because of this thermal contact resistance, the temperature drop will be there between the two materials at the interface. And the contact resistance can be obtained by using the equation like something like this. So the thermal resistance of AB contact will be given by the ratio of T2 minus T3 by Q by A. If you know the area of heat transfer, if you know the that is the rate of heat transfer and area, and T2 minus T3 or temperatures are known to us, then we can find out what is the thermal contact resistance between the slabs A and B. So we are not calculating the thermal resistance of A or B. This is a contact resistance between the two slabs because of this air gap or due to the unevenness between the two materials, because the surface is not smooth. So the thermal contact resistance is going to exist. So how to calculate that? So that can be calculated by using this equation. The thermal resistance of AB is equal to T2 minus T3. So there is a temperature drop here, that divided by heat transfer per unit area. So that is going to give the thermal resistance of AB surface, contact resistance. Similarly, we can also find the thermal contact resistance of B and C material. So B and C material combination, the contact between these two thermal resistance is given by T4 minus T5. So that the temperature drop, and this temperature drop is not much. Maybe sometimes it is 2 degrees only. Sometimes it may be 1 degree only. But that is going to affect the rate of heat transfer calculations, and which is going to increase, which is due to the thermal contact resistance. So the thermal contact resistance between the material B and C or the slab B and C can be obtained by the equation T4 RTH BC is equal to T4 minus T5 by Q by A. The temperature difference divided by the rate of heat transfer per unit area. So this is the thermal contact resistance.